All the speakers get enough time. I am Aviral Srivastav from Arizona State University. Welcome everyone to the Codes+Isss first session and to ES Week in general. We are very glad you are here. The first paper in Codes+Isss, and this is a best paper candidate, is by Flavio Ponzina. Flavio received his master's degree in computer engineering from Politecnico di Torino, Italy in 2018. He has recently obtained his PhD degree at EPFL, working at the Embedded Systems Lab under the supervision of Professor Atienza. His main research interests include edge AI, hardware, software, co-design optimizations, in-memory computing, and federated learning optimization for biomedical applications. Please. This one?
So if I do that,
Can you check?
yes, now it works. Good. Probably if I do this. Okay, so this is to go virus spoiler. Yes, not so much. So can you hear me well? Probably not so much. Yes, it's good. Okay, so I can start. Guess so. Okay, good. So my name is Flavio Ponzina. I'm a PhD student at the Embedded Systems Laboratory of EPFL, and I'm now going to present you a new paper on overflow-free compute memories for edge AI acceleration. I will start with a brief introduction, showing you the context and the main challenge that we address in this paper. And then I will present you our hardware-software co-design methodology to avoid overflows in compute memories. I will show you the achieved results and finally conclude this presentation. So we know that the main challenge in the field of edge AI is to execute compute-intense models like convolutional neural networks or CNNs into constrained devices. Now, focusing on CNNs, we know that these are layer-based architectures where convolutional and fully connected layers account for the largest fraction of memory and computing requirements. This is also visible with this plot that shows that to achieve very high accuracy, we need more and more complex models. And that's why we need optimization in this field. One way to address this challenge is by considering processing in memory solutions, where you add few logic at the periphery of memory elements. And this allows you to bring computation directly where data resides, reducing the number of data movements and allowing for a high degree of computing parallelism. When designing processing in memory solutions, you may have different choices. So you can focus on different memory technology, bringing computation in the digital or in the analog domain, and integrating the system as an in-memory computing or as a near-memory computing solution. But in all cases, we have a problem. And the problem here is that we need to perform computation using fixed bit width values. That means that we are prone to numerical overflows that can affect the quality of our output. So that's the main challenge that we address in this paper. We propose an hardware software co-design strategy to prevent overflows by constructions in compute memories. And in particular, we propose a solution which the compute memory is designed both as a near memory and as a near memory computing alternative. And we also present an hardware-aware optimization of CNN models. Now, this is a co-design methodology, and we've seen in the keynote this morning that a co-design approach is key, it's very important. And in fact, this allows us to achieve high performance and efficiency. We combine different elements. So I will tell you something about the scaling of input and output operands to prevent overflows, a corresponding hardware design based on compute memories, and a quantization strategy to improve performance and efficiency. Then I will combine all these elements together in a co-design approach to propose an overall acceleration workflow using compute memories. Going back to the previous slide, I'm highlighting here in blue the design choice in this paper. So we consider SRAM memories, computation in the digital domain. And as I said, both in-memory computing and near-memory solutions are viable alternatives. So we consider both in this paper. So let me start with analyzing the individual elements of this strategy. And I will start with the acceleration of AGI workloads. So we know, even if we focus on CNNs, that convolutional and fully connected layers, for example, account for the big part of computation in these workloads. So we want to accelerate these layers. And in the end, they can be decomposed into dot products. So this is the basic operation that we need to accelerate in the compute memory. You see, we have a series of multiplications and additions. Focusing on multiplications, you see here an example where we have two input operands, one named IMO, which stands for in-memory operands, and the other BO, as you can see in the picture, named broadcaster operands. Why? Because one of the two is actually stored inside the memory array, the in-memory operand, while the other is streamed from outside, directly inside the logic of the compute memory. Focusing on multiplication, here you see the multiplication algorithm that we employ. So you see different instructions that we need to execute. It's an iterative algorithm. And I highlighted with the different colors the basic operation that we need to implement in the logic. So you see we need additions, right shift, and negations to compute the two's complement. But what is important to notice here is that the number of instructions correspond to the number of clock cycles that we need to implement each multiplication, and it's linearly related to the number of bits, and in particular to the number of ones in the broadcaster operand. And that's a key observation. I will go back to this when I will discuss CNN optimization. But for the moment, let's focus on overflows. So when we have overflows, well, in general, we have overflows every time that the data range increases. So let's now analyze data range in the dot products that we need to accelerate in the compute memory. Consider that we use quantized data using fixed point notation with n integer bits and m decimal bits. So when we actually have to execute multiplications, our proposal is to prescale both input operands. As you see, we have in-memory operands between 0 and 1, so we only need mx decimal bits, while broadcaster operands are between -1 and 1, so we need 1 bit at least for the sign in this case, and we use in general y bits for the decimal parts. Notice that the computed products will be stored inside the memory array, so they must have the same bit width of the in-memory operand. Now, each product by construction will be again between -1 and 1. Why? Because we are multiplying two numbers, one between 0 and 1, and the other between -1 and 1. So we need to use 1 bit for the sign, and we use the remaining x minus 1 bit to represent the decimal part. But again, what is important is that in this case, the data range is not increasing, so we don't have overflows by construction if we apply this prescaling technique. Now, the picture is different when we consider accumulation. Why? Because in this case, we have individual products which must be accumulated, in general, n times. And again, each of them is between -1 and 1, but they can increase the data range of the output. So in this case, we have a number of integer bits required to represent the output, which grows logarithmically with the number n of accumulation, which is a good thing because it means that it's not exploding with the number of accumulation, but still it means that it's increasing. The data range increases. So we have overflows. And our solution in this case is to manage overflows, this type of overflows, directly in hardware. So, as I said, we consider SRAM as the compute memory in this paper. You see, we have multiple SRAM arrays connected with an H3 interconnection to achieve a high clock frequency and a high degree of computing parallelism. And we consider a near memory computing solution as well as an in-memory computing solution. Now, the near memory computing solution, the design is slightly more simpler, I would say, because the SRAM is an SRAM. So you can take the IP of that memory and just add some logic in the periphery of the memory to implement the logic that it's required to perform your computation. Conversely, the in-memory computing design is slightly more complex because you need to manipulate the memory. You need to change the structure of the memory to perform computation directly inside the memory. We exploit the concept of bitline computing, but the additional effort that you need to put here to design this solution allows you in the end to achieve smaller area and better energy efficiency. Now, I will describe first the near memory computing design that we propose. You see, we have the SRAM array and the peripheral logic that accelerate the products and prevent overflows. This is the more detailed view. Now, going back, starting from the top left, we have one register to store one operand, which is the in-memory operand. While, as I said, broadcaster operands are streamed from outside. And in this case, they are used to control this multiplexer that determines the type of operation that we need to implement at each step. We also need one register to store the individual products and another one to store the accumulations. Notice that the MAC register is a 32-bit register. And that's our solution to prevent overflows in accumulations, because we can leverage the 16 additional bits to prevent overflows by construction up to a number n of accumulations, which by definition is equal to 2 to the 16, which is a really high number. We also need to implement addition, right shift, and negations to perform the multiplication algorithm I showed you before. And notice that this circuit is not the all overhead you have to implement our solution. You still have to design your logic as a compute memory. So the actual overhead here to prevent overflows is the only part that I highlighted in yellow. Now let's move to the in-memory computing solution. In this case, it's more complex. So we'll just focus on the details of a single bit column. So you see the structure is similar to what you've seen before, at least with these colors. But again, the key here to prevent overflows is the multiply accumulate registers. So here you see a more detailed view, but again, you see there is a register to store the individual product and another one to store the accumulations. Notice that now the MAC register is split into MAC-L and MAC-H. So we actually perform accumulations in MAC-L, but every time that there is an overflow, we actually increase by 1 or -1. I mean, it depends on positive or negative overflows, the MAC-H register. So that's an overflow register, basically. And that can be efficiently done if we also store, as we do, some additional constants which store the values -1 and 1. Again, we have the circuit for addition, that's the circuit for redshift, and this is for retrieving the negation of the bit cell. In this case, the overhead to implement the overflow-free part of this design is even smaller than what I showed you before. So at this point, I've shown you how to manage overflows by scaling and by properly designed compute memories. But is there something more we can do at the application level? The answer is yes. We can optimize quantization in CNN to improve performance, leveraging the capabilities of the design compute memory. So what we propose is a per-layer quantization strategy that follows a greedy approach. So what we do is actually, at each step, we evaluate the impact on the number of clock cycles of quantizing more aggressively in-memory operands or broadcaster operands in each layer of the model. And what we do is simply applying the approach that maximizes the reduction in clock cycle. So we apply that, and we retrain the model for few retraining epochs to compensate for any accuracy drop. And we check accuracy. We check accuracy, but we also compare the obtained accuracy with a user-defined accuracy threshold. So if we meet the user-defined constraint, we just repeat the loop, trying to maximize quantization. Otherwise, before repeating the loop, we discard this optimization step, and we are not going to consider it anymore in future iterations. Notice that this is an hardware-aware quantization strategy. Why? Because, as I said before, broadcaster operands are streamed from outside, directly inside the logic, but 1 bit at a time. That means that every bit width reduction will correspond to a reduction in the number of clock cycles. So in this case, we can quantize broadcaster operands with any bit width level, because any bit width reduction corresponds to a reduction in the runtime. But in-memory operands are actually stored inside the memory array. So they can either be on 16-bit, which is the bit width of the memory word, or on 8-bit, because the architecture also supports word-level parallelism. Now, we also combine all these 3 elements together to propose an overall acceleration workflow for CNNs in compute memory. We know that we need to scale data when doing that. So that's what we do. The first thing is actually taking input activations and scaling them so that we ensure these in-memory operands are between 0 and 1. Similarly for the weights, between -1 and 1 in this case, but this operation can be done offline because weights are static data. Then we actually store in-memory operands inside the compute memory, and we stream weights to compute these operations. So we have in this example convolution, but we also have fully connected layers, in general dot products. So we use these to perform multiplications and dot products. These dot products are actually computed using pre-scaling input activations. So we need to scale them back to retrieve the expected output. As you see, we are actually combining scaling technique with the design overflow-free compute memory and optimized weights in this case. So let me now show you the results. You see, here I'm going to show you different experiments to evaluate the different aspects of this methodology. So I will focus on the hardware design, of the evaluation of the quantization strategy, as well as the overall comparison with state of the art. Now, let me start with the hardware design. We consider 6 transistors SRAMs built on a TSMC 28 nanometers technology. We support word level parallelism, and we have multiple subarrays of 2 kilobytes. The frequency can be set up to 2.2 gigahertz. So let's now compare the 2 alternatives. Here you see the comparison in terms of area. And as expected, most of the area is dominated by the memory itself, while the in-memory computing solution is slightly more compact than the near-memory computing alternative. Notice that in this case, again, the overhead that we need to implement an overflow-free compute memory is limited. It's not the whole processing element, but it's limited to less than 5% in this case. This is the energy analysis. You see the energy consumption of the memory as well as the energy consumption of the 2 different processing elements. And we measure 60% less energy efficiency for IMC. So again, IMC is more complex to design, but it allows you to achieve a more compact and a more energy efficient solution. Let me now present the evaluation of the quantization. We have a PyTorch-based environment to train and optimize the models, and these are the benchmarks that we considered in this work. So, as a baseline for comparison, we have a uniformly quantized CNN using 8-bit DOs and 16-bit IMOs, because this quantization level has no accuracy degradation with respect to floating point mode. We also set the accuracy threshold to 1%. And that's what we obtained. So for SNet 8, but these results extend to different benchmarks. So you see the bit width of broadcaster operands in different layers. And you see that we can actually heterogeneously quantize the model to improve performance. But more importantly here is that we can manage to move in-memory operands from the baseline 16-bit to 8 bits almost everywhere. So we actually leverage word-level parallelism and ultimately improve performance. Indeed, we measure 55% of performance improvement with respect to that considered baseline. Let me now compare the overall approach with the state-of-the-art alternative. So we have a cycle-accurate simulator to measure performance, as well as a C++ inference simulator to retrieve more accurate accuracy evaluations, because it implements real fixed point arithmetic. So we consider 3 different solutions. One is our proposed approach, where the compute memory has an additional register to prevent overflow. Another technique that does not employ this additional register is saturation. So every time that you see an overflow, you can saturate to the maximum or to the minimum value. Another alternative that in this case prevents overflows is by restricting the bit width of in-memory operands so that you ensure that by construction you don't have overflows in that 16-bit register. So these are the results. This plot is just showing you that we can actually leverage multiple subarrays to improve performance. This plot instead is comparing our results with the 2 baselines. So we observe that we are much faster than the 8-bit IMOS alternative because we can exploit word-level parallelism, but we are slightly slower than saturation because we consider saturate operations being immediate. So we don't account for an additional clock cycle to perform saturation. But in terms of accuracy, this is what we get. So we have comparable accuracy with respect to 8-bit IMOS, because in the end, we both prevent overflows. But saturation cannot really be a solution because it has a dramatic effect on accuracy. So to conclude, we actually propose a scaling of input and output operands to prevent overflows in multiplication, and the hardware design based on compute memory that allows us to prevent overflows in dot products. And we also propose a CNN quantization scheme that allows to improve performance. Then we also combine all these elements together in a holistic hardware software co-design approach to improve performance when executing these models in the design overflow-free methods. Thank you. Yeah, I can take questions.
Thank you, Flavio.
Thank you.
Any questions?
You used a layer-wise non-backtracking approach to quantization, which could potentially result in a suboptimal solution.
Yes.
In practice, does it, or is it benign? What were your findings on that?
Okay, so I guess that should be clear that to determine the best solution in terms of quantization bit width in each layer has a complexity which is exponentially with the number of layers, right? Because you cannot know in advance which is the best configuration that maximize that. There can be other approaches for sure. So we actually follow the greedy approach just to minimize the impact of this methodology. So we also have, it's dominated by retraining basically. So all of the execution time for the quantization strategy is just retraining. But again, in our case, it's linear with the number of layers because for each layer we determine different bit width and we just retrain for that. Every time that we find that a certain quantization level for certain operands in a certain layer doesn't work, I mean, it doesn't meet the constraint, we just discard it. And in the next iteration, we not consider that. So it's linear in the number of layers. More layers you have, more complex you have. But at least it's not kind of much more complex than that. But again, I agree that better solutions can be found in this exploration.
What I was trying to get at was, is it a good thing for other people to look at, or did it look like
Oh, yeah. I mean, you mean in different contexts, not compute memories.
Meaning a more sophisticated optimization strategy when it comes to considering the
Yeah, I mean, for sure, this is, let's say, a proposal we done based on the compute memory we design. So the bit width level that we employ is that, of course, you can stress more that step, that element in the code design we have to maximize performance, but we didn't investigate it so deeply that part. Thank you. You're welcome. Yeah, maybe later.
So, hi, I'm Christian Dietrich from Hamburg University of Technology, and I wanted to ask, I'm still missing a feeling. You need more space on your die for the circuits in memory and near memory.
Yes.
Can you give me a feeling how that relates? How many general purpose CPUs would I get when I have one megabyte? So
what do you mean with CPUs? Why CPUs?
So if I trade in the area that you propose to use in memory to have a general purpose, can you give me an idea?
In terms of CPUs, it depends on the CPU, I would say, but I can tell you that the overhead that we have for the whole thing is actually 10% in case of in-memory computing and 12% around in case of near memory with respect to a 2 kilobyte subarray. So it's not so much. Consider also that we have multiple subarrays, so you have that overhead of 10% in all subarray, but having multiple subarrays in general increases the total overhead in terms of area you have, right? But it also allows you to exploit parallelism of a multiple subarrays, right? So you can improve performance without requiring extra CPUs to do the work for that. I think there was a question here, but also there. So you can maybe both. Not forget about.
Thank you for your nice talk. My
you.
question would be, I understand you need low overhead in terms of hardware area by doing bit serial operations in memory or close to memory. But can you say something about, in comparison to other throughputs of inference per second, how do you, what is your operating points of this in memory or near memory computing with respect to other approaches?
Yes, so in general, this is not the focus of this paper. So we really, I mean, the short answer is we didn't investigate a comparison among different hardware designs. So we haven't done a comparison with the CPUs or things like that. We know for sure that if you consider quantized data, so very low bit width operands, in-memory computing and near-memory computing allows you to get maybe not, for sure, not the best throughput you can imagine, but for sure the best throughput per watt.
All right.
While if you instead you focus on something different, like, I don't know, floating point, you need for sure floating point precision in your application, probably the throughput per watt is better if you consider GPUs. But
Thank you.
Yeah. Okay.
Last question on overtime.
Okay, thank you. I'm Henri Charles from CA in Grenoble. Maybe it's a related question. Could you explain a little bit how you interact with, because you need a CPU to activate your memory computing? What is the basic idea?
Yes. Again, that was not the focus, but
Okay.
no, but I can answer also that. So in practice, this is the acceleration part that you can do in the compute memory. Of course, there should be a control around. So the control can be anything. We also know that the more overhead you have in your logic to implement fancy stuff to perform computation, the more control you need on the other side. So from this perspective, we actually try to minimize the overhead. So you see, the multiplication, for example, is not we don't have a real multiplier. We are just combining very basic operations so that it can also minimize the logic that you need to control the whole stuff. But again, we just focus on the acceleration of compute memory.
Thank you, Flavio.
Thanks to you.
Thank you. Our next talk is a CRIMP, and this is from Huai Shuo. Huai Shuo received his BS degree from the School of Computer Science and Technology, Shandong University, Jinan, China in 2019. He is currently pursuing his PhD degree with the School of Computer Science and Engineering, Nanyang Technological University, Singapore. His research interests are in embedded intelligence, neural network optimization, in-memory computing, and non-volatile memory.
Thank you for the introduction. Good morning, everyone. I'm Shuo Huai from Nanyang Technological University. Today, I will introduce our recent work, CRIMP, compact and reliable DNS inference for in-memory processing via cross-bar-aligned compression and agility adaptation. Let's take a look at what we will cover today. We will begin with the background information of this presentation. Next, we will go to related works and motivations. After that, we will introduce the cross-bar-aligned compression technique. Moving ahead, we will go to the non-entity adaptation. Finally, we will conclude with a summary of the key takeaways from this presentation. To set the stage, let's start with some background information. Currently, many DNA models have been adopted and implemented on low-power edge devices. However, DNA models are increasingly complex to gain more accuracy. Meanwhile, DNA algorithms own a high degree of computation parallelism and extensive memory size. Thus, we can use in-memory processing architecture for accelerating DNA models on edge devices. This figure shows the ReRAM-based crossbar architecture. We can map the weights of DNA models into the crossbar, and the value is represented by the conductance of the memory cell. Then the input is converted to analog value by DAC and injected into the order line of the crossbar. So the total current generated in the bit line is the product of the input and the weight. In-memory processing device can perform metric multiplication easily. It includes many parallel arithmetic units, and it manages computing in memory to reduce memory size. So in-memory processing architecture is suitable for accelerating DNA models. This figure shows an example of a convolutional layer with 6 kernels and output has 6 channels. The computing process is shown here. When map this layer to crossbar, each kernel will be unfolded into n times 1 vector and mapped to 1 column of the crossbar. If the kernel is large, it is mapped to multiple crossbars. And we call these crossbars and connected crossbars, like these two used crossbars. Then the input is also reshaped to several n times 1 vectors, and then injected into the crossbars one by one. The output of each kernel will be ANDed by the shift and AND unit to get the final results. However, crossbar has large reconfigure latency and limited write endurance. So in-memory processing devices preload an entire model into crossbars before inference. And it requires too many crossbars for complex model. Meanwhile, ReRAM suffers from some naiveness in the analog domain, leading to wide deviations in pre-trained DNA models and further resulting a reduce of the accuracy. One naivety is rate variation. Previous works has investigated huge amounts of stochastic rate variations and found that the variation follow a log normal distribution, indicating that the ReRAM resistance variations follow this equation, where R is the ideal resistance value to be programmed. R prime is the actual value programmed, and N is the normal distribution with a mean of 0 and a variance of epsilon square. Another ideality is stack and false, where some device cells are consistently in either a high resistance state or a low resistance state. Next, we will introduce the related works and the motivation of our paper. For reducing the crossbar usage, pruning methods are implied. Existing pruning methods imply backgrounded pruning, like a crossbar column or row pruning, which trims columns or rows of weights in each crossbar. And shown in this figure, it prunes a crossbar column. Then we need to remap the weights from several sparse crossbars into one crossbar to reduce the number of used crossbars. However, the remapping these two, the result from the same column of connected crossbars cannot be directly ended, like these two used crossbars. The last column of each crossbar can be ended, but the first two columns cannot be ended. So this method requires expensive extra hardware to align the output of connected crossbars. The sparsity table, the ST, is one kind of this hardware. Each one in the table means picking a number from the corresponding crossbar, and 0 means inserting a 0 into the queue. Therefore, each crossbar requires a corresponding mask memory in the ST. Meanwhile, the length of a mask in an ST equals the maximal supported pruning rate times the number of weight columns in each crossbar. So we use X to represent the unused ST units. From our experiments, the ST for crossbar column pruning brings about 44% more storage and 10% more area. The aim of training a DNN is to find the global minimum of the loss function. However, due to the flexibility of DNN weights, there exists a region where the loss function remains small, despite not being the global minimum. This means that the DNN's weights can vary without significantly impacting the accuracy. To correct a DNN that is robust to ReRAM nonidentity, some methods are proposed to use variation-aware training, which means the training method will perceive the ReRAM nonidentity and try to cover this nonidentity. It can reduce some impact, but only seals to small variations. Another type of method tries to compensate for nonidentities by utilizing extra ReRAM cells to represent the difference between ideal and actual resistance values, and shown in this figure. It can fundamentally reduce the error, but use much more crossbars. To reduce the usage of crossbars without extra hardware, we first propose crossbar-aligned compression scheme. In memory processing aware, kernel group pruning is a kind of crossbar-aligned pruning approach. It directly removes whole kernels from DNN models, and shown in this figure. Removing whole kernels means we do not need to align the output from connected crossbars. Next, we will introduce the advantages and disadvantages of kernel group pruning. Suppose a DNN model has two connected convolutional layers, denotes as L1 and L2, and we use C2 times K1 times C1 and C3 times K2 times C2 to represent the shape of kernels in these layers. The C1 is the number of channels of layer L1, and the C2 is the number of kernels in layer L1, and the C2 is also the number of channels of layer L2. So the number of kernels of layer L1 is the number of channels of layer L2. For example, in this figure, the number of kernels remained is 3. And when map the kernel into the crossbar, layer L1 is ceiling C2 divided by SBW times ceiling K1 times C1 divided by SBH crossbars. Take a layer in this figure, for example. Ceiling C2 divided by SW is the number of crossbars from column aspect this layer needs. The C2 is the number of kernels in this layer, and we left 3 kernels here. And SW is the weight of each crossbar, and it is 3. Then the number of crossbars from column aspect this layer needs is 1, and the ceiling K1 times C1 divided by SBH is the number of crossbars from row aspect this layer needs. Here, K1 is 6. It is the number of weights of each kernel's channel, and the C1 is 1. SBH is the height of each crossbar, which is 3. Then the number of crossbars from row aspect this layer needs is 2. And for layer L2, it is similar. It will need this crossbars. Kernel pruning will reduce the number of kernels in each layer. Then we use Cn+1 prime to represent the remaining kernels in layer Ln. Kernel group pruning means the remaining kernels can fully occupy each used crossbar, which means C prime is an integer times of SBW. Then layer L1 needs these crossbars, and layer L2 needs these crossbars. From the equation of layer L2, we can find the kernel group pruning also reduces the number of crossbars from the row aspect, especially if SBH equals to SBW, or C prime times K is an integer time of SBH. The byproduct of kernel group pruning in layer L1 can also guarantee that kernels in layer L2 can fully occupy crossbars from the row aspect. However, the kernel group pruning is a kind of cross-grounded pruning method. Its accuracy drop is larger than that of backgrounded pruning method, especially under a large pruning ratio. So we also use another crossbar-aligned pruning method called crossbar pruning, and shown in this figure. It removes the crossbar block weights from DN models. And we also do not need to align the output from connected crossbars in this pruning method. And both convolutional and fully connected layers can be mapped to crossbars. It can comprise these 2 kinds of layers. So the pruning ratio is higher than that of kernel group pruning. But in this method, we need a mask layer after each convolutional or fully connected layer for crossbar pruning to distinguish the importance of each crossbar. And each mask value is corresponding to a crossbar. As different layers in the DN tend to learn at different speed, the mask layer makes the model training stage more difficult to convert. Until now, we are exploring large accuracy loss pruning methods to eliminate all extra hardware and achieve low power in-memory processing acceleration. To minimize the accuracy loss, we propose a well-designed, compact model learning framework. Next, we will introduce the details of this framework by showing the changes of crossbar usage. However, to be noted, we do not need to map the DN model into crossbars during the training process. We just use an example to make this process easier to understand. The first process is kernel group pruning. Here we have an example model, and we use the binomialization layer to reflect the importance of each kernel. And this figure shows the mapping the original model on the crossbar. We first trained the model for several epochs, called initial epochs, to let all important factors have informative values to reflect kernel importance instead of randomly initialized values. Next is our zero recovery training epochs. In the zero epoch, we first sort all importance factors according to their absolute values to get the global importance rank of kernels in the entire model. During the model training process, these importance factors are jointly optimized with the model weights, and the network can automatically identify the importance of each kernel. Next, we calculate the importance factor threshold for each layer and ensure that the compact model fully occupies each used crossbar. Finally, we zeroize unimportant parts with this threshold to temporarily shield this weight for the current zero epoch. After each zero epoch, we extract a compact model and shown in this figure. Following each zero epoch, we propose a recovery epoch to allow the zeroized parameters to recover instead of being permanently removed. If any weights that are eliminated in the previous zero epoch but are potentially essential, the recovery epoch can help them escape from zero and play a critical part in the subsequent training process and even the inference process. And shown in this figure, compared to the first zero epoch, in the last zero epoch, we zeroize the different number of kernels from each layer. And the training process tries to reduce the loss for better weights. The recovery epoch gives us method a chance to learn more efficient architecture with higher accuracy. Then we will add mask layers to this model and go to the crossbar pruning phase. We propose using kernel group pruning to compress the DN first to reduce the number of mask values, which lessens the impact of mask layers in the crossbar pruning process for higher accuracy. The crossbar pruning scheme is similar to that of kernel group pruning, and it also includes initial epochs, zero epochs, and recovery epochs. After all training epochs, eliminating all zeroized weights, we can construct a compact and high accuracy model that seals the memory processing architecture value. Then we introduce our second method, non-identity adaptation scheme, for reducing the impact of ReRAM non-identity in DN acceleration. For the non-identity mitigation, we will use rate variation as an example. And for stack and force, our method can also be used. We first propose a self-compensation scheme to mitigate the error caused by weight variation. We take configuring a weight value of 182 as an example. We map this weight to 4 ReRAM cells, and each cell can represent 2 bits with a range of 0 to 3. For configuring 182, the 4 used ReRAM cells are assigned with value 2, 3, 1, 2, respectively. When directly configuring 182 into the ReRAM cell, the actual configured value is 182 under no weight variation error. However, when epsilon is 0.1 or 0.5, the actual value configured will be much different from 182 due to the presence of weight variation. Therefore, we propose a self-compensation scheme to reduce this error. Our compensation scheme is used during the configuration phase of the model to the in-memory processing device, not during the model training process. It can rely on the used ReRAM cells only and incurs no hardware overhead. The magnitude of each value on the ReRAM cell is represented in the blue box, and in our self-compensation scheme, the ReRAM identity still influences all cells we used. During the model configuration process, we start from the cell that contains the most significant bit and proceed to the cell with the least significant bit. After configuring the first cell, we read out the actual configured value and calculate the error. For configuring the second cell, we multiply the error by 4, which is the ratio between their magnitudes, and add it to the value to be configured. The new value is then rounded to the nearest integer with the range of 0 to 3. Then configure this rounded value to the second ReRAM cell. The configure process follows this procedure until all cells are configured, and shown in this figure. With our self-compensation scheme, when epsilon is 0.1, the actual configuration value is 182.03. it significantly reduces the error. This process only introduces a read operation for each cell during configuration, not influencing its endurance and no other overhead. Our method only leverages the used crossbar cell themselves to reduce the error by mutual celebration, but it also maintains the flexibility to leverage more cells to further reduce the error from non-ideality. When epsilon is 0.5, the actual configured value is 188.8. It can also reflect a significant error reduction. To further minimize the error, we can represent a weight using more cells and shown in the red dot box. Then the actual configured value is 183.08 and the epsilon is 0.5. Then we introduce the experimental evaluation results. The DNA model we used include LENet, VGG, ResNet, and IMU. The data sets are MNIST, CIVA10, human activity recognition, and ImageNet. The memory processing architecture we used is ISAC, and the crossbar size is set to 128 times 128. And each memristor cell stores 2 bits. We quantize DNNs to 8 bits and map each with to 4 memristor cells. And we use quantity and 32 nanometers to model the power and area of ST. We model the above designed configurations using a modified neural sim simulator with the 32 nanometer CMOS library. We first show the evaluation results of our crossbar-aligned compression method without considering non-ideality of ReRAM. Our method can achieve the largest weight saving and crossbar saving compared to other methods. And our method can obtain the lowest accuracy drop under almost all data sets and networks. Our method can achieve a large sparsity rate on VGG16 with even accuracy increasing. And for a large dataset like ImageNet, the sparsity rate is lower than that on CIVA10, but our method achieves a large sparsity rate and a higher accuracy. Then we show the evaluation results of the power and area consumption. Please note that crossbar column and crossbar row level pruning method needs the sparsity table for data alignment. The baseline is the original model, and the power and area consumption is normalized to the total consumption of the baseline. Our method achieves an average of total power reduction of about 4 times, and a total area reduction of about 3 times. Finally, we show the evaluation results of our final compact and reliable models. Under the condition that if epsilon is 0.1 and with stack and faults, our method can achieve compact and reliable models with a slight loss of accuracy. It can indicate that our method is a promising approach for deploying DNA models on ReRAM-based in-memory processing accelerators. In conclusion, we propose using kernel group pruning and crossbar pruning to reduce crossbar usage without extra pruning processing units. And we introduce a dynamic zero recovery training procedure, which broadens the exploration space to discover a better pruned architecture for higher accuracy and larger sparsity. We design a self-compensation scheme to diminish the error from the ideality. It only leverages the used crossbar cells themselves to reduce the error by mutual celebration, but it also maintains the flexibility to leave more cells to further reduce the error. And our method significantly reduces computing power and area. We are also producing totally compact and reliable models with only a slight accuracy drop. Thank you.
Time for a few questions. Yes.
Yeah, you can, yeah, it works maybe. So I was wondering, you are able to map all these benchmarks that you showed in the crossbars, so performing the acceleration in the analog domain with that minimal accuracy drop. So you actually map the whole CNN model into analog.
Yeah.
Okay. I was actually curious because I'm starting working on crossbars as well.
Yeah,
and we see more significant accuracy drops when moving the whole network directly in crossbars. So, for example, you're considering also IR drift currents, for example.
Yeah, because we first prune the the CN model to let it smaller, then we can map all CN models onto the crossbars. Then the crossbar can calculate the inference of the CN model, but and the identities is existing in the crossbar, so maybe the accuracy will be smaller than the trained model. But then we will use some technique like our self-computation scheme to recover the accuracy.
Okay, I see. But then this is due to the fact that you're also using 4 different values, which means kind of 2 bits for the weight, right? Which is very extreme, I would say.
Yeah, I think yes.
Okay, good to know that. Thank you.
Thank you.
Okay. If we don't have any more questions, we can move on to the next presentation. So, okay, Soyed, finally here. Okay, so this next talk is about spin-based algorithm hardware co-design for uncertainty estimation using Bayesian in-memory approximation on spintronic-based architectures. So Soyed received his bachelor's in electrical and electronics engineering from American International University, Bangladesh, with summa cum laude and university gold medal, and his master's from Technical University München with Professor Ulf Schlittmann. He is currently a PhD student at the CDNC group with Professor Tahuri at KIT. His current research interests are in robust and accurate deep learning, uncertainty estimation and reduction, hardware architectures for neural network applications, computation in memory, and emerging memory computing paradigms. Okay, I'm glad he's here. So we are on time.
Okay. Welcome to my presentation about spin bias is the aim of our topic, and which is about algorithm hardware co-design for uncertainty estimation using Bayesian in-memory approximation on a spintronic-based architecture. Machine learning approaches like neural network offer ability to solve complex tasks with high accuracy. As a result, they are widely deployed in many real-time critical decisions systems, many real-time systems where real-time decisions are made, such as autonomous driving, medical images. However, conventional neural network cannot estimate uncertainty in their predictions, which can lead to overconfidence predictions even when they are incorrect. This can lead to potentially dangerous situation in critical applications due to various sources of noise and yeah. So as a result, we try to implement Bayesian neural network, which offer a simple and effective approach for uncertainty estimations. Despite the benefit of Bayesian neural network, they are generally demand substantial computation and memory resources. As a result, implementing them in a computation in memory, utilizing emerging recessive memories such as spin transfer torque, spin orbit torque devices can inherently reduce some of their cost. Also, you can have the benefit of in-memory computation in a single package. However, implementing computation in memory in a directly to a computation in memory Bayesian neural network in a computation memory architecture has present its own challenges. As a result, in this paper, we propose Bayesian in-memory approximation approach, which allows to implement the large distribution of Bayesian neural network in the spintonic-based computational in-memory architecture. We also proposed spin-based Bayesian neural network topology, which allows efficient sampling from the spintonic-based in-memory computation architectures. Here's the outline for my talk. At first, I'll give background about this presentation, then I will talk about proposed approach, then talk about key results, then I will conclude these presentations. I'll start with the reason why uncertainty is important. Conventional neural network, which are also called point estimate neural network, which only give a single output regardless of the input. So even if you receive a data which is not from the training or the inference data distribution, for example, these are called out of distribution data, it can also give you a random input. As an example, if you train a cat and dog classifier and you give this neural network an input of a horse, it will still give you a prediction that this image belongs to either cat and dog classes. I give you another real world example with Tesla autonomous driving. As you can see, when it sees like a cart which never seen or expect during the real world scenario, it randomly gives an output. And this can lead to accidents in safety critical applications. So as a result, uncertainty estimation gives us a measure of confidence in predictions. Now I'll start with the Bayesian neural network. Bayesian neural network produces a fixed, conventional neural network produce a fixed point outputs for a given set of input. On the other hand, Bayesian neural network incorporates Bayesian method into the neural network for uncertainty estimations. In Bayesian neural network, instead of representing each parameter as a single point, so you represent every parameter as a distributions. And you learn these distributions by using Bayes framework. So you just update your prior belief, so prior probability as you see more data and to get the posterior output. And this is what basically the learning objective of Bayesian neural network is. So during inference, there are two types of inference based on how you learn it. So one is the Monte Carlo sampling based Bayesian inference. So here, after you learn the posterior distribution, so you take T sample from the posterior distribution, and on each sample, you forward pass your input. And for each T, you will get T output, and on this T output, you can average the results or do other statistical, for example, majority voting and so on to get the final output. Other approaches like ensemble-based Bayesian inference, where you have k number of ensembles and you forward pass on each ensembles either in serial or in parallel. And similarly, you can just average the result to get the final output. And of course, you can do majority voting and so on. And by calculating the variance or negative log likelihood, so you can just create, get the predictive uncertainty of each input. So the reason why computation in memory is important for neural network acceleration. So conventional computation-centric architectures are highly efficient, especially for neural network acceleration, because neural network are data-centric applications. So if you map them to a computation-centric architecture where memory and the processing elements are physically separated, so the data movement between the memory and the processing element become the bottleneck of the entire applications. So neuromorphic computation in memory, which is inspired from our brain, offers to carry out like the most common operation of neural network, like metric vector multiplication inside the memory where data is already reside. So you can alleviate this data movement, which leads to highly attractive solutions for neural network accelerations. So for acceleration, you can just map the train weight of the neural network to the crossbar arrays, where you can just encode the train weight as the conduction state of the NVM memories. In terms of memory devices, MRAM or magnetic RAM has become significant attention recently for acceleration or crossbar-based architectures. Magnetic channel junction, which is the main component of these MRAM devices, which has two ferromagnetic layers. One is the free layer, where magnetic orientation you can reverse by passing proper set and reset voltages. And another is the fixed layer, where the magnetic orientation is fixed, basically. So you can map, you can program this memory device to Lorentz system set when the ferromagnetic layer has the same magnetic polarization, and high resistance set where the magnetic polarizations are different. So you can have a binary 0 and 1 memory. And in terms of types of MRAM, so there are two types: spin transfer torque and spin orbit torque. In this paper, we use spin orbit torque because they offer several advantages compared to SOT MRAM. For example, separate read-write paths and high reading reliability, lower write currents, and high switching speed without degrading the endurance. And there are also several challenges when you want to implement Bayesian neural network. So there are Bayesian neural network challenges, and there are computation in memory challenges. So at first, I'll start with Bayesian neural network challenges. So first is the scalability issue. So as Bayesian neural network becomes large and large, and usually they have 2 to 5 times or maybe more sometimes number of memory and computational requirements. So it's become not that scalable in terms of hardware resources. And another is the quantization, because Bayesian neural networks usually require high precision memory to store their parameters. For example, if you train a neural network with a Gaussian distribution in its parameters, so you need to store the Gaussian parameters like mean and sigma for each weight. So if you quantize them and due to this quantization error, this can be a significant problem. And other is the number of RNGs. So let's say you implement the weights of the Bayesian neural network as a statistical distribution. So in this case, if you want to implement in hardware, so you have to use as much RNGs as the number of weight in the neural network, which can be millions. And as the size of topology grows, your RNG is also growing. So in terms of seeing challenges, there are other challenges like the limited precision. So spintonic, as I told you, like in general, they have only 2 stable states, like binary. And if you want to implement high precision parameters of Bayesian neural network, this is also challenging. Other is the Bayesian distribution, because crossbar structure are deterministic in nature. So if you want to implement some statistical distribution, so it's quite challenging. Other is the designing the RNGs, which is seem compatible, and this can be challenging in terms of manufacturability and so on. So in this paper, we try to solve all those problems. So at first, we propose Bayesian in-memory approximations, which enable efficient mapping of the posterior distributions. So you learn the posterior distribution, then you want to map to the SIM hardware. So how to do it very efficiently, we propose this approach. So our approach provides memory-friendly distribution, which can be efficiently mapped to ensemble from a SIM hardware. And we empirically show that this approximation leads to similar performance. I will show later in the result sections. So for our approach, so we first train a Bayesian neural network, and then we get the posterior distribution. From these posterior distributions, then we take n samples. So n can be 2, 3, or 5. So for each weight distribution, so you just take 5 samples. And from this, you have n number of weights per layer. And then you want to quantize this weight so that you can map them to like spintonic-based architectures. So quantization will discretize your like real-valued distributions, and that quantization allows like fitting the limited states of the spintonic devices. But quantization is very commonly used for all hardware implementation of neural network. And overall, after this quantization, so you have another problem that the activation distributions which will change because from the train distribution. But let's say you use best norm and it will expect the train distribution that you trained on. So to mitigate this, what we do is that after quantization, we update the statistical parameters of best norm so that it learns to be close to this quantized distribution. And then we map them to the crossbar arrays, and then we just do online operations. So yeah, in general, this will lead to like more frequent sampling from the posterior distributions because you have only n sample compared to like infinite sample from Gaussian distributions. But yeah, this commonly used in practice. So furthermore, we propose like Bayesian neural network topology for efficient sampling from the same hardware. So this shows like a general spin-based topology. And we also propose n-way Bayesian inference. And here you have an arbiter before each layer, which randomly sample like n out of like big N crossbars. So let's say you have do a one-way inference. So in this case, it will randomly sample only one crossbar out of n, and it will do this metric vector multiplication on this crossbar, and this becomes the input for the next layer, and this is repeated. But if you chose n more than one, so you take two crossbar samples, and where this metric vector multiplication is done with the same input, and at the end you average this output, and this average output becomes the input for the next layer. And then you do this repeatedly, like I showed for Monte Carlo approach, to get like T output. And on this T output, you can basically do statistical calculations to get uncertainty estimations. And yeah, our proposed topology is generalizable to all existing CNN topologies. We show only two examples, but in practice, you only need to insert a arbiter before the weight, and you also need to insert an averaging block after the weights or like layers, convolution layers, and you can just repeat this convolution layer n times to implement our spin-based topology. Yeah, we also propose Bayesian inference, the same architecture for Bayesian inference, and it implements our proposed posterior distribution based on this spin-based topology. So you have this n crossbar. You can see we show two examples of it, and each has at each cross point we have this multi-bit SOT-based cells. We also design. I talk later, and you also have the arbiter and spin-tuning-based random number generator. And for the inference, you select a small number of word lines at the same time. And this you sense within sensing circuit like analog to digital converter. And then you do this repeatedly for the other. And with the adder and accumulator block used, then you get the final output. And I will try to make it faster. And yeah, we have also proposed multi-bit structure where we quantize the weight storing the multiple cells. And yeah, number of conductor cells depends on the number of MDJ in the cells. And yeah, if you want to use more conductance, then you can increase the number of MTJs in the cells. And yeah, for our architecture, because of speed, I didn't mention. So we use like both deterministic and stochastic regime of the MTJs. So for the deterministic, we use weight storage, and for the stochastic, we use the RNG implementation. And by changing the input current for this RNG, you can like program the switching probability. Now I'll give you briefly our K results. And we do detailed evaluations on semantic segmentation and classification tasks on different data set and different topologies. And our proposed spin-based network perform comparable to the state-of-the-art with up to 1% improvement in the accuracy. And as you can see on the Cambridge dataset, the prediction map is also similar to both state of the art, also ground truth value. In terms of uncertainty estimation, when compared to state of the art method, the proposed method produces significantly better performance on different uncertainty estimation metrics with up to 20% improvement. And it also produces superior semantic segmentation mark. So for semantic segmentation task, you want to look at this correctness map, which shows like the white as the correctly classified pixels and black as the incorrectly classified pixels. And like an ideal Bayesian neural network should be uncertain around incorrectly classified pixel and very certain around correctly classified pixels. And so as you can see, for our case, most of the uncertainty around incorrectly classified pixels. And another sources of uncertainty due to the lack of data is, for example, in Cambridge, compared to other classes, you had like bicycle and pedestrians as number of intensities a lot smaller than like sky and grass and street. So you want to be highly uncertain around this too. And our proposed method also captured this type of uncertainty. In terms of energy consumption analysis, our method produces 80 times better energy compared to FPGA implementation and 35% compared to like RRM, and 3 times better when compared to MTJ-based methods. However, note that our proposed method requires only 3 RNG respective of the model size, but related works, the number of RNG increases with the depth and width of the network. So in terms of memory overhead analysis, so memory requirement is an inherent drawback for, as I mentioned, Bayesian neural network and ensemble method. And yeah, this becomes the scalability bottleneck. In our method, we use 4-bit quantization, which also implicitly a model compression technique. And with this, we are able to achieve up to 8 times reduction in the memory consumptions. So in conclusions, uncertainty estimation is vital for improving reliability of neural network predictions. And Bayesian neural network offer an efficient approach for uncertainty estimates, but implementing them in a computation memory offer several challenges. So we propose Bayesian neural network topology called spin-based, which can be implemented on SOT-based computation memory hardware. And we also propose Bayesian in-memory approximation method for implementing statistical distributions in computation in memory. We also propose multi-value SOT-based pitch cell to map quantized parameters, and our method enhances the prediction performance 1% approximately. It can detect 100% out of distribution data, which I couldn't show here. Please look it into our paper. And in terms of hardware overheads, yeah, we have 8 times smaller overheads and 80 times smaller memory, and 80 times up to smaller energy consumptions. So thank you.
Thank you for your presentation. I like your usage of Bayesian neural network. Can you comment on a little bit about, was your experimental data just for the semantic segmentation, or we did classification also?
So we used 2 classes. One is like autonomous driving. So I show Cambit, and for biomedical segmentation, we also use skin cancer, I think, and skin lesions detection. But these are like a binary semantic segmentation, and this is much harder because it has like 24, I think, classes.
A follow-up on that, the reason I ask, when we compare the Bayesian neural networks under this uncertainty, you have this data to be already known. Have you compared with conformal prediction using as a methodology? Because there we don't need any dependency on distribution, or if you can comment on that, how you would scale the same idea onto conformal prediction. Thank you.
Yeah, it's a good question, because conformal is a different kind of way to determine uncertainty. Like these are distribution free uncertainty estimation method. So what we use is like variational inference, which is very commonly used for Bayesian neural network. So like if you use Markov chain Monte Carlo, you cannot train it on big network or big data set, but variational inference allows this. So this was the benefit we use. But in future, I think we can look into this. And yeah, this is a nice questions.
So fundamentally, you increased the uncertainty classification estimation by 100x, right? As one number that you
Yeah,
showed.
we can detect, for example, we did experiment on 6 out of distribution data. For example, we inject noise, like Gaussian noise, into the training or like testing data. So in this case, the distribution would shift from the original distributions. And then, like I showed one example that neural network train on, let's say, I showed example on like toy example, like cat and dog, but we use like benchmark data set on CIFAR10 and this kind of thing. And we use other class like SBHN and street classification data set. So on this, let's say, which is different from your training data, how much it can detect. So we use some sort of a matrix. With this metric, you can say, okay, if the uncertainty is bigger than this matrix, then I say it's out of distribution data, and is smaller than this matrix, then it's in distribution data, which my model knows this.
I see. Okay. Okay, perfect. Okay, so let's move on. Thank you, Soya. Okay, our last talk for today is a late breaking paper. So this will be a 5-minute presentation, right? So we'll do 4+1, 4 minutes of presentation, 1 minute of Q&A. Is that okay?
I haven't prepared for the allocated time for questions, so my presentation structure to be around 5 minutes.
Okay.
So
we
plan
can-
for questions at the poster, but we can do whatever. I can speed it.
That's a good point. So yeah, please speed it up. And after this session, we have a extensive poster session and we can ask authors all the questions that we like. So let me quickly introduce Konstantinos Balaskas is at KIT and he received his BSc degree in physics and MSc degree in electronics and communications from the Aristotle University of Thessaloniki in 2018 and 2020. He joined KIT in 2021. He is pursuing his PhD in the chair for embedded systems. His research interests include approximate computing, hardware-aware machine learning, and DNN accelerators.
Thank you for the introduction. So hello, everyone. I am Konstantinos Balaskas, and I will be presenting you our work titled Differentiable Slimming for Memory Efficient Transformers. Oh, okay. Okay, starting with our motivation, we know transformer models have been achieving state-of-the-art performance on a wide range of tasks, especially on the neural language processing domain. However, they are usually large models come with immense computational complexity, so it is very hard to deploy them on resource-constrained embedded devices. To do that, a well-known technique, as we saw also in previous presentations, is pruning, especially importance-based pruning, that promises to alleviate that complexity and boost the memory efficiency of the models. Related work on that subject follows mainly 2 directions. Training techniques usually employ multiple stages, that incurs a large overhead in training time. However, post-training pruning is mainly limited in terms of memory savings, mainly because of accuracy constraints. So in our work, we try to bridge the gap between the two, propose a single-stage pruning-aware training technique, incorporating this importance of components, and leading to higher memory efficiency of transformer models. So at the core of our technique are structural modifications to the classical transformer architecture. These come in the form of gate parameters at the output of 2 different blocks of the transformer. First, we talk about multi-head attention blocks, or as we call them, heads. So the alpha gate parameters, and at the output of layers from the encoder or decoder blocks, or the beta gate parameters. Now, the larger the gate parameter is, the higher the value of it is, the higher that the contribution of that block is to the final output. So in this way, the gate parameters control the information flow of the output of that specific block. We apply on top of the parameters a softmax function. In this way, we are able to learn the relative importance of one component compared to its counterparts. This is done in a fully differentiable way, a minimal overhead on the training time, and facilitates our single-stage training scheme. This training scheme consists of two steps. First, the weights get updated to minimize the training loss. We all know this. And then the gate parameters to minimize the validation loss. We interleave these two steps and are left with a set of optimized gates that follow the weight distribution afterwards. We also apply structured dropout to avoid any local minimum on the training loss. And after training is done, we are left with these components that we know their importance and can prune away, starting from the more redundant ones. This leads to different models of various parameters in terms of memory that can fit diverse memory budgets. So for our evaluation, we used the classical transformer architecture and focused on the neural machine translation task with 3 different datasets. The blue score is our accuracy metric. And for comparison, we use the classical transformer architecture with magnitude-based pruning and the state-of-the-art approach that uses post-training pruning based on component importance. First, before getting the evaluation, here are some results showing heat maps of gate parameters. The darker the head, the higher the importance is. And as general observations, what we see is that even though for different tasks, different datasets, different heads come off to be more important, usually only one is the one that drives the output of that block, meaning that only one head is actually needed for this task that we studied to drive that output. We'll see that come to play into the later slides, and these are some head pruning results. On the right, you see the blue score, our accuracy against an increasing number of removed parameters. So we observe from these models that the blue score of our models in the green line are almost equal to that of the unpruned ones, meaning that by doing this training, we are able to retain accuracy levels. However, our low performance drop reaches only 16%. And as you see that this trend is not maintained on the state-of-the-art models. Moving on to layer pruning, which is a more difficult task to do, or depth slimming study of our work, we mainly observe that decoder is a much more important component, meaning that when we prune away component in decoder layers, accuracy is being degraded. This reaches unacceptable levels for the state-of-the-art. However, we see in most cases, our technique is able to also prune away some of decoder layers after the encoder is fully pruned. This accuracy gets really degraded when the full decoder model is pruned away. This summarizes our results. And to conclude our lightning talk, we have modified the transformer architecture with these trainable gate parameters. That is, we are able to learn the component importance. This is done in a fully differentiable way without incurring any or even minimal overhead on training time. We saw that pruning away multi-head attention blocks really retains the accuracy level of the unpruned models, whereas pruning away layers has some degradation in terms of accuracy, which is smaller compared to the state-of-the-art when we reach higher pruning levels. As I said, this was a lightning talk, so for more questions, please visit us at our poster session or come find me and visit our webpage. So thank you.
We were fast, lightning talk.
Lightning talk.
Okay, could you comment a little bit on your fully differentiable, right? So what makes this part non-fully differentiable?
What makes it non-fully differentiable?
Yes.
It is fully differentiable.
Right. That's what, so you carefully chosen the words, right?
Okay, fully differentiable basically in that context means that the gate parameters are optimized by the optimizer when we do the training. I showed here a two-step approach, meaning that while we have the weight parameters that drive the computation, we also have the gate parameters that control this output flow. This is just an additional step for the optimizer. So this is immediately done with back propagation. Everything is optimized with back propagation. That's what makes it fully differentiable.
Okay. Any more questions? Oh, okay.
So the next question I have is for your results. So basically, I just see that here, for example, but also maybe in the next slide.
Sure.
It's the same. Sorry, sir. So you see that basically your accuracy, I would say, when you don't remove any parameter, is lower than the other baseline. So I was just wondering why, if you don't remove any.
Yeah, excellent observation. if you remember, I said that for layer pruning, we also applied structure dropout. That by default reduces some of the accuracy of the baseline training, meaning that we train and then we prune. So when we train, we have no removed parameters, which is the leftmost side of the figures. And because we have added structure dropout in our training compared to the state of the art, we have some reduced baseline.
There's no structure.
On the head pruning, no, because it's more unstructured than this, and we didn't need this structure. But was to kind of alleviate this really drop of the accuracy. But great observation.
Did you try making filters orthonormal before pruning?
I did not, and I don't know how to do that.
I'll talk with you or your sometime later at the conference.
Please explain.
Posters are the perfect place to be there. Hey, thank you everyone. And hopefully I